Thank you, Professor Inman. Well, thank you all, but I must say that there's a couple of things wrong here. My introduction is wrong because what I am the luckiest man I've ever met, and I'll explain why in a minute. The second thing that's wrong is the title of this lecture, and you'll see why the title is wrong also in a minute. But let me begin by telling you why I consider myself the luckiest man in the universe. When I was a young person, younger than you guys are, my dream was to have a role in the design of something that flies. I used to look up at airplanes and said, I'd die happy if I can say I designed the left bracket on the right engine nacelle of that airplane. Well, that didn't happen, but something even more exciting happened. In 1986, I joined 20 people in Washington that were trying to build rockets. And one day in early 87, I had an idea. A couple of years before, the United States Air Force had shot down one of their own spacecraft by using a very, very small rocket launched from an F-15 fighter aircraft. The satellite P-59 something or other was actually a heliophysics satellite that was in excellent working condition, which made the heliophysicists rather hopping mad. But I figure out that why use a narrow-launch rocket for such a destructive purpose when you could possibly use it to launch a satellite? So a friend of mine claims that this idea came to me on April 8th, 1987. But unfortunately, the original drawing, which was not on a paper napkin, it was on a yellow ruled paper, is lost to history and mankind. But this is the earliest picture I can find of a Pegasus sketch. I had both a big version and a small version, and it's dated May 27 of 1987. Well, I was lucky that I was surrounded by people who believed in the idea and were smart enough to find private money to develop this rocket, because this rocket was developed entirely with private funding. And one thing linked to another. After a sketch, the first engineering drawing, so we're now all the way up to March of 1988. And of course, this led to a patent. And you see that in the patent, the carrier aircraft is a B-52, because by then we had contacted NASA, who used an old Air Force B-52 for its X-15 program. And we lucked out that they had just unmothballed that aircraft for a F-111 escape pod parachute research program. The F-111 pod was killing pilots left and right. And they allowed us to use that B-52. Pretty soon, drawings and analysis led to real hardware, and real hardware led to test. Another reason that I feel extraordinarily lucky is that not only I work on the paper side of the design, but I actually had a physical hand in putting the rocket together. That's yours truly here, torquing a jack that's going to move the 3 degree of freedom dolly that holds the rocket to these 4 hooks under the pylon adapter of the B-52 aircraft. I remember that day vividly. It took us a long time to get that puppy mated, but finally we did it. And soon enough, we were doing the first captive carried tests with an inert model, and that is the B-52. And I love flying. As Professor Inman said, I did fly our little 310 from Leesburg Airport to Willow Run. I always loved flying, so I figured out, how can I finagle my way into the B-52 on the day of the first flight? And then I had a brilliant idea. At the time, nobody had done a safety analysis of how risky it is to light a 40,000-pound rocket close to an aircraft. I mean, people have launched air-to-air missiles and little thingies, but nothing this big. So actually, I did it. I remember writing a little MATLAB existed then, unbelievable as it may seem. It was an early MATLAB, no graphics. So I did a little simulation of the particles. There's 2 different models of how a rocket motor explodes. There's the sausage model, and then there's the balloon model. So anyway, I wrote this analysis, and I determined that the separation time had to be X meters, 300 meters, So it took 5 seconds for this thing to drop 300 meters. And then I said the magic words. And to prove that I am very confident of this analysis, I volunteer to fly on the aircraft. And the most amazing thing is they believed me. Now, being a NASA aircraft, I had to have proper training. And this was early 90, and it was pretty cold. The water temperature was so low that you had to have water survival training. And here's my colleague Bob Richards and yours truly at Miramar Naval Air Station, Top Gun. And this is the dreaded dunker that they put you in there. It simulates a helicopter cockpit. This thing drops into the pool. As it drops into the pool, it rotates. So you end up strapped on your seat, upside down, underwater. And then you have to escape out of there 3 times, the 3rd time with a blindfold. It was so much fun. And here I am, dressed in full regalia. Now, some of you may remember a famous Stanley Kubrick movie that features a B-52 as a star. And the name of the movie is? Dr. Strangelove. And all of you remember the famous scene where Major Kong... is there too much light in here? Well, hopefully you can see this. Drops from the B-52. So 2 days before the first flight, my boss and mentor, Dave Thompson, shows up at the hangar where we're assembling the rocket with a cowboy hat in his hand. And I say, oh no. And he said, oh yes. Now, if you look closely, notice 2 things. You cannot notice the 3rd one. I'm very carefully have my flight boots away from the rocket. I'm sitting on an anti-static mat, and I have a wristat on my right hand. I was taking no chances. But finally, the day of the first flight occurred. It was April 5th, 1990, 3 days short of 3 years from the date of that first sketch that somebody claims that I had put together. I don't think it will ever happen in my lifetime again. But here's the first flight. Now, this is a frame from a 16-millimeter chemical film movie that a chase aircraft took, and they just happened to hit the very instant of ignition. So, to my knowledge, there is no picture like this anywhere where you see the beginning of the plume of a large, solid rocket. Now, if you notice carefully, you'll notice that both the other chase aircraft and the B-52 are climbing at a pretty steep clip. And here's where you see the power of marketing overpowering the power of engineering. The original clip was this. The aircraft are in steady state flight. This thing is falling down like a rock. And it's only the lift of the wing. This thing goes from Mach 0.8 to Mach 2 in about less than 10 seconds. So it accelerates a very good clip. But you can't sell a rocket that fires going down, and that's why they turn the film around. Now, that's nothing compared. The best moment of my life was this. The day we received from NORAD the 2-line element set of a rocket that I had designed. If I had died that day, I would have died a happy man. Anyway, just to give you a little feeling for my credentials, why I think I'm kind of semi-authorized to talk to you today. So let me go to the second thing that's wrong with this lecture today, which is a title. The title talks about space transportation. On the next few slides, I'm going to proceed to demonstrate to you that there ain't no such thing as space transportation. There is rocketry, and there are space launches. Now, if Benjamin Franklin were to be writing to his French friend a letter today, he would have told him that there's only 3 things sure in life: death, taxes, and space launch. Because, after all, space launch is awful. It costs money. It is the second fastest way of destroying in the least amount of time the most amount of value, second only to nuclear explosions. You know, it doesn't do anything useful per se. As a matter of fact, it is a recurring theme that space launch is too expensive. You open any publication in the field, and you see things such as, oh my gosh, we're spending all this money on space launch. What this country needs is a $29.95 launch vehicle. That theme has been repeated over and over and over again. In 1987, we started developing a small rocket. Were we the first small entrepreneurial company to try and do that? Oh, no. I gave a similar lecture to this in 2005, and for that lecture, by the way, that's the other thing that space launch does that you want to avoid, but anyway. In 2005, I prepared this list of companies that had started for the purpose of developing a small, low-cost commercial launch vehicle. These were the companies still in business in 2005. This was a list of companies that started but did not exist anymore in 2005. And by the way, here we are, Orbital. And you will notice the absence of a company called Space Exploration Technologies. It wasn't in my list, and I don't know exactly when Elon started SpaceX, but it certainly was not in my list today. But Amarok was there, Aeroastro, Beale, Andy Beale, remember Andy Beale? Oh boy, a number of them. Now, I redid this list in 2013, and the still with us is down to 15, of which several are actually making a decent living building things other than space launches. And there's only two, Orbital and SpaceX, that are alive. And of course, the list of dead small entrepreneurial space companies has increased. So what's wrong? What's going on? Well, there's several things that are going on. So let me introduce to you the enemy. Now let me explain why this is the enemy. What do you see in here? You see a bunch of vehicles that are obviously in space, right? There's a planetoid of revolution, and there's something else in here. So they're obviously in space. But they have wings. They have large aerodynamic intakes. They look pretty beefy, so they look very solid. So the secret must be in the specific impulse of the engines. But look at that. They all have their z-axis in the same direction. Why? I mean, it's definitely not the direction of gravity, because it's obviously the primary attractive body. So if they were, zenith up, they would be that way. And here's the problem. People associate space with aviation, with aircraft, with aeronautics. And that association, that parallel, has caused more damage, far more damage, than it has caused good. Let's face it. Orbiting is getting enough speed so the curvature of your trajectory, as it's curved by gravity, happens to be approximately the radius of the Earth. So all you need is acceleration. And good old Isaac knew that. Let me give you some numbers. Suppose you wanted to carry 1,000 pounds 1,000 miles. And you do it with a barge, railroad, a truck, an aircraft, or you put it in a satellite. And I'm going to measure the energy required to do that in arbitrary units of gallons of gasoline. Gallons, imperial units, oh dear. But and this is the speed roughly associated with each of these modes of transportation. I'm going to divide that energy into cruise and acceleration. Now, a barge is second only to pipelines in terms of energy efficiency of transportation of matter at a certain distance. The energy associated with the acceleration of a barge from 0 to 5 miles per hour is so small as to be buried in the significance of those digits. Now, as you go to faster means of transportation, the ratio of acceleration to cruise, gets worse and worse. As a matter of fact, for a 747, that goes 1,000 miles, well, I've cheated a little bit here. I've included in the acceleration the cost of climbing to altitude and so on. But now you go to a satellite, and oops, it's all acceleration. There's zero cruise. So is transportation really, is space launch really transportation? let me give you a comparison here. To the left, you see a picture of the world's largest operating power plant, which is in Bruce County, Canada. It has 8 reactors. Efficiency of a nuclear power plant is about 0.3. So to produce 4 gigs electrical, it has to produce 14 gigs thermal. If you just compute the thermal energy produced by the 2 solid boosters of the shuttle, they don't last too long, last a few minutes, but during those few minutes, it's producing over twice the thermal power of Bruce County Nuclear Power Plant. I take another example. The Saturn V at liftoff was generating as much thermal power as 14 Bruce County nuclear power plants. And ladies and gentlemen, this is the problem with space launch. You are handling incredible amounts of power. Not for long. 10 minutes, 5 minutes, tops. But during that period of time, you're handling, in a controlled fashion, unimaginable amounts of energy. So let's go back to the transportation analogy. Here's Soyuz, a fine spacecraft to carry astronauts to orbit. At liftoff, a Soyuz carrying 3 astronauts is producing as much power, again I'm using thermal, as much power as 98, count them, there's 98 747s that total 40,000 seats. So try again on me this analogy between aircraft and rocketry. It just isn't there. This is not the only big difference. I present to you here a tally of every single, the count per year of every single attempt, successful or unsuccessful, launched to orbit from that famous day in 1957 to, I have a version that goes to 13. Now that has a 13 data on it. And you can see that the count follows the fate of geopolitics. When was this thing started and when did it have its peak? Around the time of the Cold War. As the Berlin Wall fell down, the rate went down, had kind of a minima around 2000, and it's picking up a little bit. But in the best case, we had about 142 launch attempts a year. Down to, there's one fatal year, 1986, in the United States, where there were 9 launch attempts that year, and 3 of them failed, including, unfortunately, Challenger. So we're not talking about, there have been some sporadic spurs of activity. The GPS development did include a lot of launches, and the good thing about those launches is that they were very similar one to each other. There have been little spurs of activity when commercial constellations, there was this bunch, the 66 Iridium spacecraft were all launched in 9 days over 1 year in 14 launches using 3 different launch vehicles and 0 failures. That's my little Iridium flash joke here for those of you who are amateur astronomers. So that's the first enemy, is a comparison of rocketry and aviation. Let me present to you the second enemy. And this starts my tally of potential ways of reducing the cost of launch, increasing its reliability, and ending world hunger. So what's the first idea? Well, we're technologists, aren't we? So let's use technology to lower the cost of launch and increase its performance. Well, let me be a little bit more specific. The reason I had an iPhone in there is because we're all familiar with what's called Moore's Law. Here's Gordon Moore himself, a founder of Intel, father of very large-scale integration processors. And Moore's Law says that every 18 months, the number of transistors or active devices per unit area doubles and doubles and doubles. And there's plenty of statistics. Here's a tally of number of transistors per chip log against year of introduction, and it keeps improving, and that's what makes iPhones possible. Now, if you look at the fundamental laws of physics behind semiconductors, and you look at what could possibly limit the size of the features on an integrated circuit, you'll notice that you have many possible flips of Moore's law available before we start hitting some fundamental physics limits, such as the principle of uncertainty or quantum physics. Before we start hitting there, we have a bunch of 18-month doublings available to us. There are other areas of technology where there has been a similar improvement, but much less dramatic. I plot here the history of cruise-specific fuel consumption versus year of introduction of jet engines, and there is a moderate trend, nothing as dramatic as this one, but there is such a trend. So the question is, do we have a similar situation with rocketry or launch vehicles or not? Well, the first thing we have to figure out is what is the figure of merit. In Moore's law cases, the number of transistors per unit area. What is the equivalent measure of improvement in performance in rockets? I'm going to offer a very simple one, but in my experience, the most satisfying one, which is sheer size. Because after all, rockets are handmade. We only make half a dozen of them a year. A visitor to Orbital once commented to me that upon close examination, your rockets look handmade. I said, well, guess what? So size and mass is a good avatar for cost. Pegasus was a cute little rocket, weighed about 20 tons, 40,000 pounds, and today we can sell one for about 20 million. We originally thought we could sell one for 6 million. We didn't quite make it. So 12 was the next price, but it was 20 years ago. There's inflation, taxes, the economy, sequestration, and all this stuff. But you go to larger and larger vehicles, including this very interesting one. You look at Saturn V, and that was a 2,800 metric ton vehicle, cost about $1 billion each. I'm comparing it with a Bainbridge class destroyer that the US Navy has a bunch of. It's a little bit taller or longer than Saturn V. It's much heavier, over 3 times, but it's less than twice as heavy. Only one other advantage, it lasts 25 years, not one flight. But in any case, I'd like to propose as a metric for improvement or efficiency of space launch, the ratio of the size of the vehicle to the payload it carries. The other thing you have to consider is that this guy had a little bit more payload than this tiny little fellow there. So let me offer G over P, G being the gross lift-off weight, P being the payload. Both G and P are dimensional quantities, but G over P is non-dimensional. And now, let me share with you my most deep secret. I'll be glad to give you copies, but trust me, everything I ever needed to know about rocket science is in this page. And essentially, this is a very simple hand 4-function calculator way of figuring out the G and P of a multi-stage rocket, given the G over P of each stage, and the G over P is given by this simple little formula. I wish this would be called the Elias Equation, but yeah, somebody else already invented it, so too late. And S and R are 2 very simple parameters. S is what's called the structural mass fraction. Other people use fuel mass fraction, but we can have an argument over beers as to why we should look at S and not F. Of course, S is 1 minus F. And that's simply the total structural weight of the rocket divided by a structural weight plus a fuel weight, whereas the gross lift-off weight is S on F plus the payload. And R is a number that depends on the total delta V that that stage provides and the specific impulse, which is simply how much thrust you get for every unit of mass that you eject out of your rear end. So, to give you some idea, a structural mass fraction of 0.2, 20% is, yeah, easy, I can do it, no big deal. 0.1, man, awfully hard. In terms of specific impulse, you have to make a distinction as to what propulsive technology you're using. Solids, liquid propulsion other than LOX hydrogen, and of course there's this hybrid thing that has the worst features of both solids and liquids combined in one. And the only other thing to remember is that staging is your friend, because this leads to an exponential relationship of G over P with respect to delta V. So you get this little effect that says if I have a single stage, my G over P goes like this as my delta V goes up, and I have to go to 9.9 here. So if I want to go single stage to orbit, man, you're in awful trouble. I chose 345 seconds of ISP and 0.5 structural mass fraction, but other than that, this plot just plots the previous page. But if you divide your travel into 2 stages, each of them is an exponential, so you end up at a reasonable G over P for a pretty decent delta V, whereas on the single stage, you'll go, pardon the pun, ballistic. So now let's look at a few historical launch vehicles and see how they score on the G over P scale. Here's a bunch of vehicles that share the same characteristics. They're medium size, and that affects their structural efficiency. They all use LOX kerosene. They're all 2 or 3 stages. So it's not a surprise that they're all around this line, this area. This line here is simply the statistical fit of all those numbers. These are the real thoroughbreds. Atlas 2A, for a small launch vehicle, one of the highest, best, remember, better is low, one of the best G over P's ever. But the Atlas was a very, very high-tech vehicle that had its own problems and used LOX hydrogen like crazy. The other interesting vehicle is a Saturn V, huge, so its structural mass fraction was very good because there are economies of scale. That's why this line kind of gets better with size. And 2 of its 3 stages were LOX hydrogen, big time LOX hydrogen. Third vehicle I like to point out, Space Shuttle. Blech. Why? Because every time it went up, it had to carry all the stuff it needed to come back, and that cost a lot of mass. Moreover, the shuttle was not entirely reusable. Those big solids were not reusable, they were recyclable at best. But you can see what reusability costs. And there's more to reusability cost than just the penalty in mass fraction. Not only it is heavier for the same payload, but that mass is more expensive because you're not simply building thin little aluminum tanks that you don't mind if you throw them away. You have to use very expensive, sophisticated thermal protection system. You have a very complex landing mechanism or system. So reusability costs a lot of money. Now, let's take a look at the 2 fundamental technology parameters that explain this image here. Let's first look at propulsion, specific impulse. As I mentioned, it depends on whether you're talking about LOX hydrogen, LOX kerosene, bipropellants, hydrazine and nitrogen tetroxide, or solids. So each of these families have a line. And here I've actually plotted actual historic examples of propulsion systems and the year when they first flew. And as you can see, we reached the climax in propulsive technology with the Space Shuttle main engines. These were the most efficient, best thrust-to-weight ratio lift-off. You know, there's electric propulsion, but it doesn't work for lifting off from the ground. When did that happen? Mid-70s, late 70s, early 80s. Since then, nothing has happened. Why? Because if you look at the fundamental way a rocket engine works, think about this. If the conversion of thermal energy into mechanical energy is governed by Carnot's law, the efficiency depends on the difference in temperatures between the high temperature reservoir and the low temperature reservoir. What is the high temperature reservoir on the rocket engine? The combustion chamber itself, which is at a hideously high temperature. And what is the low temperature reservoir? Vacuum, 0. So there is no thermodynamic machine in existence that can come close to the efficiency of the rocket engine. So the rocket engine is, from a machine and thermodynamic standpoint, uses 98% of the available energy in the covalence bonds between hydrogen and oxygen. We're there. We've reached the asymptote of physics. There is no Moore's law ability in propulsion, in chemical propulsion. We're there, and we have been there since the mid-70s. Let's go to the other one, structural mass fraction. Again, to do this analysis in an honest way, you have to divide the pieces of the rocket in various types. Boosted cores means a lightweight core like the Ariane 5 surrounded by two big solids. Since the solids carry most of the thrust, that central core can be very light. So boosted cores tend to have a very low structural mass fraction. At the other end of the spectrum, upper stages tend to be small, so they have diseconomies of scale, and tend to have a lot of garbage on them, like computers and IMUs. So they tend to have poor mass fractions. The average mass fraction of a rocket is a composite of lower stages and boosters and upper stages and so on. But the most efficient stage ever built was in 1956. And if anything, not only the trend lines do not go down, if you think about it, they're actually going up a little bit. So to summarize, we reached the peak of technology in specific impulse in 1981 with the Space Shuttle main engine. I can't pinpoint to a specific law of physics, except perhaps poetically invoke intercrystalline forces in the behavior of materials. But the best ever entire launch vehicle mass fraction was 0.067, and it was the Atlas in 1959. Why is the trend negative, that is increasing instead of going down? Because the Atlas was such an incredibly thin aeroshell structure that it had to be pressurized for it to even keep itself alive. There's a famous grainy black and white 8mm movie of an Atlas at Vandenberg Air Force Base whose pressurization system failed while they were fueling the rocket. It's kind of heart-wrenching to see the rocket crumble in a typical Prandtl column compressive instability, textbook case for structural engineers. I took one still from that grainy film. It's starting to bend right here, and that's because the pressurization system on that very thin shell. So we don't build rockets like that anymore. All right, so I give up on technology. What else can we do? Well, we can make it reusable. What a novel idea. Nobody ever thought of reusability before. The only problem with reusability is that practice, theory and reality sometimes collide. This pair of pictures I'm going to show you are famous. They've been used all over the world. But it shows the artist's conception of what a space shuttle orbiter processing was going to look like in a conventional hangar. There's people on the floor, and there's some GSE, and they're putting a satellite in here. Big deal. This is what the OPF, Orbiter Processing Facility, looked like. Can you see the orbiter there? Let me help you. Here's a nose. There's a payload bay in here, I think. I'm not sure. I've been there myself, so there's an orbiter there, I may assure you. Now, NASA did not start the shuttle program without realizing that there were some challenges. As a matter of fact, critics of the space shuttle program point out to this 1972 study by a company called Princeton Econometrics, later known as Econ, and usual setup here, guys. Morgenstern was a professor at Princeton and a principal of the company. Poor Klaus Heitz was a grad student. He did all the work. but there's both of their names in here. Does that sound familiar? So they were given the task by NASA to analyze, you know, we said earlier, if you make a launch vehicle reusable, it's going to be heavier and more expensive, and you're going to have this huge non-recurring cost. But hey, if you use it over and over and over and over again, maybe it makes sense. You can recover it. So here's the question. How many flights a year do you have to fly for a reusable launch vehicle such as Space Shuttle to be cost competitive with an expendable launch vehicle such as the ones that had been flying at the time? And this is the key chart, the key graph out of that study. And they go through a number of scenarios about cost of money and inflation and this and that. But let me point out two items in this plot of interest. The area that they're studying is a number greater than 600 and smaller than 736 flights in the time period 1978 to 1990. So they're debating whether the shuttle was going to have 50 flights a year or 60 flights a year. And boy, you know, it makes a big difference between 50 and 60. You know, we're not exactly sure it's going to work. Is it going to be 50? It's going to be 60. Back to my plots about the history of rocketry. Here I have added to the bars you've seen before this black line that limits the data to US launches. And superposed on that, this dashed line is a 3-year window averaging smoothing of the failure rate. I had to smooth the failure rate because the raw data is so noisy it would hurt your eyes if I plotted it raw. It does deform the data, as those of you who do filtering for a living every day. It doesn't phase shift it because it's an averaging window, but it does reduce the amplitude. 1986 was that year, that horrible year that I mentioned, when the US had 9 launches, 3 failures, so a 33% failure rate, and one of the failures killed 6 people. So this would be the 50 to 60 range, the sweet spot of full reusability. And of course, this is what the shuttle produced, 4 to 5. And now we look at the numbers that the US is launching, and we're talking about 20 launches a year. So that's why I claim that reusability is not the answer. We'll never get, see, for reusability to work today, and by the way, I forgot to say something. In 2003, Orbital and 5 other major aerospace companies were given money by NASA to look at the second generation RLV. Our statement of work did not require us to redo the econ analysis of how many launches a year you need for reusability to be useful, but we did it anyway for us. Now, would anybody care to guess what results in 2003 we obtained? How many flights a year do we need for reusability?
25.
Let me give you a hint. Has specific impulse or structural mass fraction changed since that study? 50 to 60. Because the fundamental parameters haven't changed. So why would the result change? Okay, so people never learn. I'll let you read that. Now, maybe what he's saying is, I'm going to build a rocket so cheap that I will have 50 to 60 launches a year. But he's not saying that. He's just saying somebody has to invent a reusable launch vehicle. And if you do that, we got cheap launches, reliable launches, we end world hunger. So the reality is that it doesn't work unless we go to 50 to 60 a year. Well, perhaps we could come up with a novel configuration. I should be very careful in criticizing others because, after all, I came up with a novel configuration. But that was the theme in the 2000s, which led to a curious phenomenon which I call it's a B movie, okay? Color by Photoshop, music by Dan Golden. DCX, Kistler. Remember rotary rocket? Hey, you guys should like this one. It has a rotor. I saw the prototype of that thing out in Mojave. You probably also did, Carlos. X-33 Venture Star. I can't even remember what this one was. All right, let's keep at it. Come on, there's got to be other ways of reducing the cost of space launch. How about simply sell a lot of them? Well, the only problem with selling a lot of launch services or launch vehicles is that you have to have somebody that buys them. So, let's be a little bit more technical here, is what is the price elasticity of demand of space launch? Well, to do that, you have to look at who will give you money to launch something. And let me show you, as a frame of reference, what the Satellite Industry Association, which is the U.S. Trade Association, analysis of 2012 commercial space worldwide revenue, and they sum it out to $190 billion a year. Now, this analysis has to be taken with several grains of salt because they mix a lot of things in here. For instance, they consider that the business of direct TV, some of you may have direct TV dishes at home, is part of space. And it is true, it is a service, television programming, that comes to you thanks to satellites. Those satellites had to be launched. And indeed, if you think about it, this is the world's largest market of space services. They also include other comms, VSAT, very small aperture terminals, point-to-point, the transmission of the World Cup from Beijing or whatever to here. They include the whole world industry of GPS receivers as being space activity, and other ground support equipment, ground antenna systems, everything. Now, in this big pie, look where satellites are, and look where launch vehicles are. Tiny, tiny little part. I have some caveats here, like it doesn't include classified expenditures, but you don't have to be a rocket scientist to figure out they're in the 30 to 50 billion a year. And by the way, this US 2.2 billion, it's all defense and intelligence. We have no commercial launches in the US. Well, we just had two, thank you Elon Musk, SES-8 in December and Tycom 6 in January. By the way, both of them Orbital built satellites. By reference, the entire worldwide space industry is less than half the size of Walmart. If that doesn't put you in your place, I don't know what will. Now, I can go through a variety of examples. I've looked at a typical military space program, and a typical military space program launches 18% of the total cost of the program. Now, everybody knows government budgets are limited by the budget. So, to first approximation, if I reduce my launch cost by a factor of 2, I've opened up 9% of the US government budget in military space, so I could expect my demand to increase 9%. So, reduce price by a factor of 2, increase demand by 9%? That doesn't look very elastic to me. I go through the same argument with a typical NASA space science program. Now the launch cost has gone down to 10% of the budget. Direct TV, the big gorilla that we saw earlier, launch 4%. And it's not just me, okay? If you don't believe me, fine, but a very reputable company, Futron, in Washington, D.C., more than 10 years ago, analyzed the business of VSAT, very small aperture terminals, and concluded that launch cost represents 3% of the cost of providing VSAT terminals. So where is this demand going to come from? Oh, I know what you're thinking. You said, Antonio, come on. You left off the big market. Space tourism. Well, voila. These are all the space tourists that have ever been. Now, one of them flew twice. This guy liked it, so he flew twice. But the fact is that in 9 years, a total of 8 seats were sold. And by the way, none since 2009. I don't know, must be something in the air. The last paid price, so the one we should use as a reference, was $40 million in 2009 for approximately 2 weeks in orbit. But the cost was really in that big energy you need to get to orbit alive. I say alive because if you're willing to go to orbit dead, there's a couple of companies that for $5,000 will fly your ashes. We've done that. We've been the host of some of those. The total revenue that this market, remember we were talking about billions and billions of dollars, 120 million revenue. However, what's really worse is that these 8 seats were flown in 3-seat spacecraft, so there were actually shared rides. They shared the launches with 24 other seats, and they shared the production with 60 seats. So they reached this very, very low number. Have you ever paid $40 million for a ticket? Thanks to the co-production. By the way, NASA bought 24 seats from the Russians in 2009 for $51 million each, and people criticized NASA left and right, but actually it was a good deal because they were not flown in 2009, they were for future flights. So if you do a little present value calculation of this money, it was a good bargain. I mean, that's an excellent number. So is there really reduction in cost as you go up in numbers? I did a little analysis of an example that irritates the U.S. Air Force a lot, which is for the 10 years between 2004 and 2013, Ariane 5 has flown 54 flights, has produced all this capacity to geotransfer orbit for this total amount of money paid by customers, an average of $21,000 per kilogram. By comparison, 39 Atlas 5s and 23 Delta 4s, so smaller, comparable total number, produce this amount for this money, so an average of 58 to 66. Some of that difference I can explain by noticing that Ariane 5 is one service, one rocket, one company, everything is focused. Whereas the United States government, in its infinite wisdom, decided to split the market into 2 vehicles that compete with each other with 2 different production lines. Well, they have a common factory, but that's okay. 2 infrastructures, 2 everything. So about 1/3 of the difference between these 2 costs I can instantly attribute to just the fact that they have 2 instead of 1. The rest, I have to wonder, and I don't think for a minute that European engineers are any better than U.S. engineers in terms of efficiency. There must be something else. Maybe it's this magical thing called competition. And in the interest of time, I will gloss over this chart that shows the relationship between actual, honest-to-goodness, properly computed launch reliability. And by properly computed, I mean you can't say that a rocket flew 3 times, all 3 times it worked, therefore it has 100% reliability. You have to use at least the simple, dumb Bayesian probability formula. K is the number of successes, N is the number of trials. If you use Bayesian probability, then this is a trend line, and these are the actual cases of relationships between number of launch attempts and Bayesian calculated reliability. And you can see that shuttle is right where everybody else is. For all the money that was spent on the shuttle, it has a reliability very much in family and in line with everybody else. So what else is there to do? Well, let's harp back to this plot and say that, well, at least we can improve things if quantities increase. They're not going to increase by factors of 10. but they could improve by a factor of 2. And here's my third and last version of my history of rocketry chart, where I color-coded the size of launch vehicles that have been flown throughout the years. And of course, in the early days, most, if not all, launches were of the class that today we call medium. Delta II was a medium rocket, doesn't exist anymore. Atlas was a medium-class rocket, doesn't exist anymore. Titan II was a medium-class rocket, doesn't exist anymore. That's interesting. 3 of them, and they don't exist anymore. And indeed, these are the yellow lines, and look at the yellow lines. They're getting fewer and fewer and fewer. And what's happening? People are putting satellites on bigger and bigger rockets. So what's happening to the number of launches? Fewer and fewer. So my message to the powers to be, and this is a mantra that I've tried to repeat in Washington over and over again, is please start designing missions for the good old reliable medium-class rockets. If you do that, you will triple the number of US launches, because for every launch you get out of an ELV, you cause 2 more launches to happen on the medium-class vehicle. Will that reduce the price or the cost of launch by a factor of 10? No. But it could by a factor of 2, and that's probably all we need. But more importantly, reliability will increase significantly because people will be sharp, the teams will be up to speed. So that's what I usually, that's what I just said. Now, is there one more? Unfortunately, yes, there is one more. Sheer willpower. I am smarter or harder working than those fat, lazy idiots before me. And to that, I offer Dave Aiken's Law of Spacecraft Design number 19, which says that, chances are that you're not that smart. If your terminal velocity turns out to be twice the speed of light, it's more probably that you screwed up your calculations than that you've invented warp drive. So the sad message is that all I've told you is known. I haven't discovered anything. I've just fished things out of the closet and presented them to you. These are things that have been known for years. But unfortunately, we have things such as this. This is a quote from Dan Golding on the PBS NewsHour. I have the transcript. I couldn't find the video, but this is an actual interview. Look what he says. I am absolutely convinced 10 years from today, so 2006, we will improve the reliability of launch by a factor of 100. I mean, how you can statistically measure that? We don't have enough launches to reliably measure 1 in 100 with any degree of confidence and improvement, and cut the cost by a factor of 10. When the NASA administrator says that, what does the average citizen think? What does the press think? What do the politicians think? Well, he must know what he's saying, doesn't he? After all, he is a NASA administrator. It is depressing. So I'd like to finish my remarks with a number of quotes. Let me first quote the great Arthur C. Clarke. In a different context, I'm going to take his quote a little bit out of context. He says that any sufficiently advanced form of technology is undistinguishable from magic. And that's a problem we have today. 99.9999% of the people that whip out an iPhone from their pocket hasn't the foggiest idea of the miracles of technology inside here, the high efficiency, low noise gallium arsenide ultra high frequency or L-band front ends, the self-putting to sleep, self-cycle counting CPUs that reduce power consumption, the lithium-ion batteries. For those individuals, this is magic that exists. So don't tell me that magic doesn't exist, because it's a piece of magic. So somebody comes to them and says, I can build a launch vehicle that is 100 times more reliable than the ones today and costs a tenth. Well, it's another piece of magic, just like this, right? You can't tell the difference. So here's my next quote. And I just made this up. So here's the quote. But seriously, as we keep progressing in this modern technology world, distinguishing magic from bullshit, or innovation from bullshit, telling magic from non-magic becomes harder and harder. And it requires knowledge, it requires skill, it requires education, it requires experience. Very few people have it. You have it. You have the smarts. You're getting the education. You will be getting the experience. If you don't tell everybody what the difference is between magic and bullshit, who will? So my parting words to you is another quote, and I've been very careful to find out the exact source and who exactly said this. So this is a very accurate quote. Stan Lee was, of course, the creator of Spider-Man. And this is my message to you. Don't, and please exercise great responsibility. Thank you.